been focusing on cognition and decision models because cognition and decision models, especially decision models, has some very well established paradoxes, like those abnormal phenomena, and that's really resisted a coherent explanation for decades. So it sounds like a very productive direction to attack. And we believe it can be, at least I believe, and it's being worked on right now, applied to many other fields. Like I think this was raised as a question in the previous session as well, like AI, machine learning, large language model. But in general, right now, some of the computational cognitive scientists are trying to work on like all kinds of cognitive models with large language model, like including the Bayesian, of course. But yeah, that's a very new frontier of the work, I believe. And so my work is roughly maybe in 3 sections. I first of all say, why. Emmanuel has done an excellent talk about why. So I want to quickly review with a few very, very everyday, very, very simple examples. So human behaviors are probabilistic and dynamic. So we need tools to understand them better beyond our natural language. And if you want to build a formal system to model those kind of behavior, then you can use classical probability or quantum. So most of the work have been based on classical probability. But of course, gradually I learned there are many other probability theories as well. But majorly, the field of cognitive science has been built on classical probability theory. And quantum probability actually is just, as viable as possible. So like quick review about the history of it. So because most of us, including myself, has only been trained to take it for granted, right? We only in the mathematics classes, in the statistics classes, and we are being tutored to classical ideas, probability theory, and we take this as if they're true, and this is the only way we can use to model the human behavior and the world. But classical probability theory really involved over several centuries, and first actually was in response to problems in physics, of classical physics, and then accumulated in the 30s last century, and an axiomatic foundation of the theory didn't exist actually until 1933. Actually, it's an interesting year, 1933. In the book by Kolmogorov, so that's why also sometimes people call classical probability theory the Kolmogorov theory. So the foundation of the theory of probability. So in a very oversimplified way to say that classical probability theory is based on the premise that events are represented as subsets of a larger set called the sample space. And you use an additive measure to assign probability to the events. Then this kind of, using this subset to describing the events actually entail a logic of subsets, and oversimplified way to say that it's equivalent to Boolean logic, but there are more generally speaking, is the sigma logic. So Boolean logic includes some very strict laws, and we are very familiar with this maybe from elementary school, like the closure axiom, the axioms that events are commutative and distributive. So for example, the commutative means probability of A and B is the probability of B and A. So the order shouldn't matter. So, but is this the only way to think about events and probability? I thought so, because I didn't know whether there are other alternatives. This is just something I was learning in school, and the only thing I was reading, and I never really thought about whether there are other ways. So, but if we read more about this, especially we have so many scholars and the most influential scholars here actually right on the panel and in the audience too, very familiar with the history of science. And we know actually we look at the history of science, it's never the case, right? Even the geometry, we thought there's only one theory of geometry, but now we know there are many. So that's the same with the probability and actually beyond the classical probability theory and the quantum probability theory, there are many other probability theories too, and new ones being developed. So what's the quantum probability theory? The brief history again, it's just like the classical probability theory. It was coming from the physics, right? So the quantum mechanics was invented by maybe one of the most brilliant group of scientists, one of the most brilliant people. And in the 1920s, in response to those very paradoxical findings in those empirical data, in experiments, and I think Michael and Jacob in the mathematical tutorial workshop in the afternoons have been talking and go over some of the experiments that inspired the development of the new theory. So like this is a famous picture, maybe one of the most famous picture in science history too, is this, I think it's 1927, the Solvay conference, which was in response to this newly emerging quantum theory. And it's always fun to take a look at those people. I think by my counting, there were 29 and 17 have won Nobel Prize, or later on won Nobel Prize, and including, of course, our powerful and very role model of this female scientist here. Curie won actually two Nobel Prize in two separate subjects. But anyway, that's a different story. So here, if you're interested in look at this, actually, this is the conference that some of the very interesting and famous conversation debate occurred, especially between, I think it's 27, I forgot the age of Niels Bohr at the time, but anyway, this is young Niels Bohr, if you can see it's on the, at the end of the second row here, and Einstein, which is taking this most central position there between them. So I think it's this very, if you have heard this conversation, it's at this meeting, I remember is that Einstein wasn't happy about Heisenberg with Heisenberg again, all these emerging young people, Heisenberg's uncertainty principle, and said, yeah, God doesn't play dice, right? So you probably have heard the story. And I love the Niels Bohr's response. Niels Bohr said, well, don't tell God what to do. So I guess this may be connected with, resonates with a lot of interesting discussion we had in the past few days from our speakers. So, but anyway, with this quantum mechanics, quickly, right, maybe just as the Solvay conference as actually turning point, it has the instrumentalist camp of the physicist at the time has been maybe winning the debate, and the theory has really developed and totally changed the world. Give us transistor, give us the laser, give us a foundation of chemistry and so on. But what's interesting is that even at the time, this group of brilliant physicists didn't realize that in inventing this new theory of physics, they also invented a new theory of probability and mathematics. And this wouldn't become clear until in 1932. Actually interesting, if you remember the year for the Kolmogorow's book, actually it's 1 year before his book, that when Norman published Mathematical Foundations of Quantum Mechanics, which give axiomatic foundation for the theory. So later, and Feynman has suggested this can be used for quantum computing, building quantum computers, and so on. And we know those have been extremely influential nowadays. So what, again, in very, very oversimplified way to say this. So quantum probability theory is based on the premise that events are represented as subspaces of vector space. Then this entails new logic, the logic of subspaces. So it relaxes some of the axioms of Boolean logic. But of course, it adds a lot of other restrictions to a theory as well, which maybe we can discuss more at 1 o'clock or tomorrow. Like tomorrow afternoon, I will review more empirical data and models we are doing. But today, my purpose is to show the general idea and some of our early effort, and especially I want to very pragmatically show how we can show this model is useful compared to some existing models that's already there, so well-established models that's there. So this new logic relaxes some of the axioms, like including the closure properties, commutativity, and distributive laws. So, but again, right, this is more top-down, like Emmanuel was mentioning. It's like, oh, the math is beautiful, let's use it. But it's not just so, right? But because also bottom-up, the field of human observables, the human science, the social science, human behavior science needs this kind of new framework because there are accumulation of puzzling results. We can't use a coherent theory to explain anymore. So I want to give a few examples here. So like human cognition really seems to demand those kind of relaxation. But again, I want to, emphasize that it's not just more general, more relaxed. It's highly testable. I will show that today. And actually, there are some similarity between the two theories, but a lot of difference. And so our challenge to find those empirical data and paradigm and maybe come up with innovative ways to test those ideas. But anyway, but at least there are some concepts that are really, really intuitive. I think Alex Wang also said this on the first day, and in numerous talks he and I had, that it's so intuitive. How can it be otherwise, right? So when you take the quantum leap or somehow like the theory, it's just so natural with our human thinking. So, but anyway, so here let me show you two very simple everyday examples. So like the principles from quantum theory resonates with those deeply rooted psychology, intuition, and conceptions, like especially like the uncertainty, ambivalence, and so on. So I want to use like two examples. One is a concept from the theory called superposition. And it really, really is a good way to conceptualize and formalize ambiguity, uncertainty, this deep uncertainty we feel. And the other one is something we talked a lot, is at the center of the theory in a way, that's complementarity. It shows how constructive our judgment, our human measurement, our language, and our thinking can be. So first, let me show this superposition idea. If you haven't heard this is like, let me give you a very simple example we use all the time. So for example, if you have been a juror, in America, you call down juror duty, and you have to judge whether the defendant is guilty or innocent, right? If you're doing this from the classical perspective, the classical information processing, a classical theory perspective, then what this really does is something like over time, the error is the error of time. You can think the person, hey, the evidence, maybe at this time, here's this evidence from those two sides, I feel, and with my own thinking, I think it's guilty. And at another time moment, you hear more from the defendant, maybe now think, oh, the person is innocent. So you just between the black and white, because right now you're doing a binary choice. So you jump between this guilty and innocent, guilty and innocent at a time moment. And it can be continuous time if you do those continuous dynamic models. But from quantum information perspective, it's quite different. So this is a simple idea about the superposition idea. is that our beliefs or our judgment or our this mental state don't jump from state to state, like from the clean black to a white to clean yes, no, clean guilty and innocent. But we experience a really deep uncertainty, right? We just feel fuzzy. I don't know. Both sides sound like reasonable. Yeah, maybe sometimes here, sometimes there. We feel that deep ambiguity about all the possible states simultaneously all the time. So it's not a combination about distribution, about how likely is guilty, how likely is I. It's really this fundamentally, in the way the person itself is kind of, enabled to know the full information and feel this deeper ambiguity. And then, but you have, so that's why we say you have potential of both states at each moment. So in our quantum theory language, it's like you're neither feeling guilty or innocent. You're not in one of the states or have percentage or have probability at the combination of states. You just add both states, literally, in a way. Literally, I don't mean, again, at neural level or physical level or some other level. Okay, here I'm just using this black box to know the process. So maybe sometimes you change there's a potential. So there's a way of the quantum theory, we can compute how strong is the potential, but it's not a probability yet. It's the amplitude probability, it's a potential. So you have this shades of gray, shades of color, but you're not in the black and white. So this is quite different from the traditional thinking, or maybe the major thinking in the field of cognitive science in modeling those kind of uncertainty. So that's superposition. Let me give you another simple example about the cognitive or communication or any kind of social measure. Our social measure can create rather than record what in the human, right? So this goes to this complementarity question, a concept that Emmanuel has mentioned a lot and give a lot of good examples here. So this basically really is a good way to formalize. Formalize means use mathematical and computation language to formalize this constructive view of judgment. So constructive view is quite well accepted, I think, by many social behavior scientists, and of course by our very prominent scholars here, many. So, but right, but this is because in psychology, this is because we have limited mental capacity. We can't store everything in our brain, right? In our mind, and we want to reserve resources, and maybe there are efficient way to rotate perspective. It's just impossible. So actually, we had a lot of good discussion in the past few days and today at Emmanuel's talk too. It's just like all this problem, like quick, slow. We have to use heuristics. We have to use when you're less familiar, it requires more resources. It requires more capacity. It's harder to rotate your perspective, like from thinking for yourself to thinking for other people. So many key concepts in psychology actually it's very constructive in nature, but when it stayed at the verbal theory, it's hard to test sometimes, and sometimes when the theory itself actually is saying it's constructive, but maybe the model actually is not constructive, it's quite fixed. But anyway, so let's take a quick simple example again. Suppose you're trying to understand the emotion you feel. Like emotion is very constructive, right? So a lot of classical theories, like the early ones, like 2-factor, 3-factor theories of emotion, really was, in my opinion, really is constructive view about how we construct our emotion, how the emotion evaluation, assessment can be contextualized. So if you feel some feelings, and from the classical perspective, this really was assuming we are always in a definite state with respect to the possible measurements. Like for example, the measurement can be, are you happy? Rating from 1 to 5, right? Typical emotion rating. 1 means you're not happy. 3 means yeah, comme ça, comme c'est. Like my daughter always use French to answer me, comme c'est, comme ça. In the middle, like kind of mixed, and maybe like I'm not sure, ambivalent, and then the last one maybe you're very happy. And take a measure. For example, the similarity, and now our example is emotion, but you can be any example because those kind of verbal language measurement is just prevalent in any of our human research. So what this says that actually I ask you a question, then you trade what's in your mind at that time moment, and you tell me. So it's kind of record what's in your black box. From the point of view, it's different. Yeah, it's fuzzy, it's indefinite. But when you impose a measure, it's much like, yeah, you collapse that wave function. Well, if you're doing, yeah, you could use wave function in your model, but anyway. So the idea here is that you impose a measure, whatever the measure is, this measure actually quite critical because we have our work to show that change the measurement really essentially change what people reporting. But of course, people always know measurement is important. There are many people specialized in study psychometrics, for example, different theories of measurement, like item response theory of measurement and so on. And this is such a problem. For example, I will show you the public opinion research that Emmanuel mentioned later on today. So yeah, we know, like actually public opinion research people totally know measurement is like has problems, right? So that's why we always do representative sample, try to get more people and randomly split the sample so we can measure, different orders of the question because we knew they might have influence on people's answer. But typically this is, treated as a problem we have, right? So like then we would, for example, in public opinion research, then we average out this two samples data, then hopefully cancel out the average out or cancel out the differences. And this is the same for like experiments too, right? That's why if you do experimental research, in human experiments, we always try to do, for example, random assignment to different treatment to different conditions, because we know that could matter, right? You treatment 1, treatment 2, or treatment 2 and treatment 1, and so on. So, but anyway, we know this problem, but typically this goes to those variants we don't want to apply, right? In those models, typically it's those things we try to, call it error, like error. But I think from a point of view, it's essential. It's like really critical. It's not an error. It's like really important part of our review, important data to reveal our human nature. So it's together with this system and impose of the measurements can create a definite state, bring into existence of reality that was not there. So this is kind of similar to, the physics in this conceptual level. It's like, it's this measure, but of course it's a good question. Maybe I think that'll bring up like, what's a measure, right? We'll talk about that. That's a really excellent question. In social science, it's different from physics. So I feel like as we talked earlier this morning, I think social behavioral science faces the even more challenges to be creative, to develop things that's not there in the physics yet. And maybe we can help enrich the theory. And maybe the theory, I guess, in a way, it's not really belong to physics, right? Just like the classical probability doesn't belong to classical mechanics, like this doesn't belong to physics. And there are a lot of ways we make the theory maybe more general or develop new experiment paradigms that can fit the way we test a human because we can't put people in a vacuum space, for example. We have too many random variables. So, okay, but let's go back again. So this is about, I want to show the complementarity, this idea, or compatibility, this idea has a very important intuitive psychology, maybe, relevance here. And actually, if you look at the history, it is, in fact, it's very interesting. So this distinction between compatible and incompatible variables, measurements, observables, is really critical for quantum theory. As Emmanuel has mentioned, has shown. But it's also interesting, actually, if you look at history, actually Niels Bohr introduced this concept to quantum theory. But actually, he imported this from psychology, from William James. If you are familiar with literature in psychology, actually, William James is one of the founding fathers of psychology. In 1890, in his book, actually, he already used the word compatibility, compatible. So it's Rubin. If you study psychology, you may recognize Rubin is the scholar, studies the Rubin-Vaz phenomena, bistable perception. You say it's Vaz, you say it's phase, like those kind of bistable. It's actually being empirically studied by Harold Altman-Sparker, the speaker from our first day, empirically using the quantum approach now. But anyways, Rubin, who is, I think, a family member of Niels Bohr. I don't remember their relationship right now, but that's Rubin, I think, and that's Niels Bohr. Hard to find the old picture. Sorry, it's blurred. Like have both in one, because if you don't look into history, you never would imagine they're related. But anyway, they're related. Actually, it's Rubin, as a psychologist, introduced the idea to Bohr. So it's really Bohr chose something from psychology to quantum theory. So in some short papers, we argue that we should introduce the concept back to psychology and so on. But people have been doing a ton of work, and this nice work reviewed by Emmanuel early this morning really is based on the key concept about compatibility of the variables, your measurements, your observables. And this is very useful and very testable in our in physics and also in our current work as well. But also, again, I want to emphasize that, at least I believe, is a way human social behavior science can maybe pay back to psychology, to physics, because I think in a lot of ways, right, so physics has the theory of truth, the reality and the world and the universe. I think somehow the psychology is studying the observers, right? When we're looking at the universe as observers, really, there are a lot of concepts actually can be reached in a human paradigm, in our human data, our human theories. So maybe this also is an indirect response to the last comments, the criticism from last session, which is excellent. What's new here? I think there are a lot of ways we can say, but I think there are new ways that we believe we can pay back to maybe the general concepts, some of the general concepts in the quantum physics. So these are just the two examples. There are a ton of other examples, and again, the beauty of the theory is that it's axiomatically based. And not only is the concept and the theoretical ideas less coherent, highly tested already in physics, but it's also providing a self-contained, coherent, and importantly, axiomatic mathematical foundation and computational tools for us as researchers to human behaviors, to observers. So now, we use those tools, those concepts and tools to formalize our current, maybe extend or specify our current verbal theories in in our field, like in decision, in communication, in political science, in behavioral science. And then that's up to you, right? Your specific question you're studying, the kind of phenomena you're doing. So, but I have to emphasize again, like Emmanuel already mentioned a couple of times already, this wasn't an easy task. It's not that if you are so well trained in physics, quantum mechanics, then you can easily come up with idea or ways to test it. I think it's really highly interdisciplinary. I think because I see Professor Hoffman was here, he called for the help from brilliant people come to join the team. I want to took the privilege to do the same. Exactly. We needed the people from those truly interdisciplinary questions. These people, the team built from really the different fields to work on the the true, like most important theories in separate fields, but apply those tools. And also it's not just simply application, because when you develop, it's just the classical computing models. It's not just a simple application of the classical probability. You have to develop those ideas, use the tools to build up your new house, your new headset. I'm just trying to steal the metaphor from Professor Hoffman here. The new idea, this new like folder, whatever, to look at the word. But anyway, the strength of those kind of formal theory, I think as Professor Hoffman, as Professor Pathius has mentioned, it just makes it very testable and falsifiable. And why this is more so maybe than some other theories is because I hope to show a little bit using the limited time. That is because the quantum theory, at least in our past, our groups, past 15, 16, like two decades of work, is trying to pour a lot of phenomena that's really hard to explain using a coherent framework. But now we can use really very simple a group of rules to explain a range of very different phenomena that have never been even collected in the literature before. So I think that's one way to show the strength, not only just how good the data can fit, right? How good we can fit the data using our model, but also theorize-wise, like cognitive theorize-wise, to be able to have a theory that's generally applicable to a range of phenomena. Because as Emmanuel mentioned, with those abnormal paradoxical findings in the literature, in the decision-making, for example, the fallacy, when one come up, there's always a ton of many good, useful, interesting theories come up and try to explain them. But they kind of, like as Emmanuel said, as Band-Aid or the patches, try to solve the one at a time, right? But because it's not more broadly applicable. So yeah, but the quantum theory, like this is just really dated, even limited summary. It has been used as the same framework, explaining a large group of phenomena that have never been explained in the literature. And I highly recommend you read Emmanuel and Busemeyer review paper, annual review of psychology, published last year, that has a really clear list of reference of a range of phenomena. But there can be many more, like application to the generative AI, to large language models, to those really big frontier questions right now. I think that's another way we can try to work with. So I guess I will go quickly. Let me see the time quickly here about the probability theory. So yeah, you can see with the classical theory on one side, quantum theory on the side, they were very similar, just with some difference in the notation and some difference in the rules. So, and I know some of you have been attending last year in prior years, or this year, to Michael and Jacob's workshop in the afternoon. Hopefully you got some of the ideas. So I want to show you some examples. I want to quickly go through those. So I want to maybe just stop here to just quickly mention something Emmanuel said, but maybe it's worthwhile to highlight this again, maybe with my application example rely on this. So from the classical, sorry for the typo, classical theory, right, it's based on the Boolean algebra, the probability of events A and B and probability B and A should be the same. Like, for example, Emmanuel mentioned like a person being a feminist and bank teller, right? The probability shouldn't matter based on whether it's A and B or B and A because it's a subset, it's a logic of subsets. But the quantum theory is different. It doesn't have this conjoint probability. It's really collapses this sign, this state, to project this on the subspace of B and then A. It has order. It has a sequence. If you ask a B question first and then A, if you think about B first and then A, if you think about whether it's bank teller or it's a feminist. And so that's the way you take the squared squared length of this sequence, the projection. That's how you compute the quantum probability if you have been attending the workshop. But anyway, this doesn't matter. But I would just want to say the order matters. How you think about two words, two measurements, two observables. So it's different from when you start from psi, this stage, to think about A first and then to think about B. So that's a point. And you have a way to compute it in the theory. So I want to really quickly go over this. How do you do, right? Like there were so many good theories, like Emmanuel mentioned in the early days and even now too, for people in psychology, for example, and for most part of social behavior science, maybe people do not do like computational models, like mathematical models of those theories, if it's based on Weber theory. And maybe that goes to, Professor Hoffman's comments from yesterday's afternoon, some of the theories, we don't know whether it's right or wrong because maybe likely right, maybe likely wrong, because sometimes it's hard to test. So I want to show how we tested those things, a few ways at least. So again, going back to one example, and I will show a range of many empirical examples tomorrow afternoon, and the way we build up those kind of models in more detail. But now I just want to quickly go over this idea. So now I kind of regret to say it's question order. It's not really question order, right? Like Emmanuel had reviewed, it's a question order, but really it's measurement. It's a sequence of measurement problem, actually. Just like in physics, we have the measurement problem here. So in a lot of phenomena, we know this already. It's like in the literature. So like, for example, in the survey research, people, as I mentioned, they just split the questionnaire. So it's interesting to observe those phenomena because it's always very interesting to see, voila, there's all the effects. Interesting, right? So again, this is the first example I was looking. So actually, this was what inspired me, kind of low-hanging fruits that Alex has been encouraging everyone to think about. So this was the low-hanging fruits for me. Why? Because when I think about how I find the empirical data to test those ideas, I say, yeah, measurement, right? We have measurement problems. So it's so easy, like order makes difference in quantum physics. The order of the measurement should make difference in our social behavior science. So actually, I'm not a public opinion researcher. That's like really a group of brilliant people who develop survey questions. But anyway, so then what I did is that, okay, let's just let me Google and do the search in my library database, say what question order effects have been studied. I knew those. I knew because this is just so common. But I just look at it, people have been describing so many, so interesting. So then I found a ton of literature on this. But then I focused on the survey research because at the time I talked with the prior like what president or vice president of Gallup research. David Moore, who has been done some really interesting summary about the order effects in public opinion research, right? From his experience, he summarized all kinds of patterns, very interesting, 4 or 5 different factors. So, but anyway, so I got some of this data actually from Gallup poll in the initial states. So one of those is this: do you generally think Bill Clinton is honest and trustworthy? How about Al Gore? Do you generally think Al Gore is honest and trustworthy? How about Bill Clinton? So this is from 1997, when the candidates from the same party, from Democratic Party, was being surveyed during this national representative sample in the United States. So this is the results. If you're asking in the Clinton and Gore, that's what you got: 50% trust and 60% trust Gore. But in the other order, you can see big difference, right? So if they knew this ahead of time, you can manipulate public opinion survey. So that's something hopefully we never do. Actually, that's some of the books have been published by public opinion researchers, especially those practitioners, such as how to steal an election, like those kind of things. You can manipulate public opinion in some way. So you can say those are big differences, right? Like if in a now comparative context, when it's asked first, actually, the Gore is really have an advantage, but then it's being put down to 60% when it's following his question following Bill Clinton. But anyway, you can have a lot of explanation about this, but that's not the point. The point is that the classical probability theory cannot explain this if you go with that. As Emmanuel also showed, because the subset, probability of A and B, should be the same as probability B and A. It's from the same sample space. So of course, you can say maybe it's not from the same sample space. Then that's a great question, and exactly. And that's another way to do it. Then you can have some space here, some spaces there, right? It's kind of, you can use Bayesian to say given is AB order, given is BL order, but maybe that's too descriptive. Didn't really explain those mechanisms here. So, but the quantum representation of the events and subspaces, and now we come to the question, it can be compatible or incompatible. How do I know they're compatible or not, right? So in this example, what's compatible means the two events can coexist. In psychology, idea is that the order doesn't matter when you ask the two questions, have the two Clinton and Gore, which in our example, it means people can think about both at the same time. Like really they think about, I trust Clinton, I trust Gore. And for some people, probably it's very true. Maybe they are extremely supportive to both candidates or to the party, and they just like, 100% I'm trust both, right? So then they're compatible. And two events may be incompatible, right? If incompatible, then they can't coexist. I feel that's the case for me, at least, right? Because I don't really think about whether I trust Clinton or not. I don't really think about those questions all the time, because maybe there are questions much more kind of fixed. Like, for example, if you ask me my age, but actually that has become constructive nowadays when you're getting older, I noticed. But if you ask me, for example, do I love my family? Yeah, 100% yes, right? So it's just very certain. This is now uncertainty. But I think for most of the things, we do not want to use our very valuable limited resource to store those things, right? To think about this thing. And it's impossible anyway. And we construct them at the time. And typically they are a little bit ambivalent or uncertain. So incompatible is possible. So then empirically, how do we do it? Empirically, we just test typically whether there's order effects. Now, in our example, we knew there's order effects. Then we have to use this incompatible representation. So that's how we decide in our modeling whether something is compatible or incompatible. So, it's a really good discussion already in the prior talk by Emmanuel and during the question session, is that those probably much complex, this compatibility idea probably is much more complex and challenging in social behavior science than in physics. Physics can be manipulated, it can change. It's different by people, it's different by the questions, by the measurements, right? It's just much more complex. So, but anyway, in general, incomparability can be a useful new concept we use to consider those kind of modeling in psychology. So, and of course, this is consistent with this constructivism in psychology. And a lot of people, like for example, social psychologists have been studying those as well, and have done very interesting work. And actually, I think it's also useful for us to look at their paradigm, empirical paradigm, and see how we can model those ideas. But anyway, right, it's very straightforward. The idea constructed from the first question or first measurement can change the context for you to think, to evaluate the second measurement, the second question. So it's causing the sequential effects, this order effects, because you're not thinking about both. You're not thinking about Gore and Clinton at the same time. So this is a very intuitive idea. But then what quantum theory really does, so that's why quantum theory is not competing with those verbal theories typically, right? It's really, because verbal theory, you can formalize it using classical models, different classical models, and you can use it to, you can formalize those verbal theory using quantum models and different ways too. Actually, even in quantum model, there are different ways you construct your model. You know, different groups have been doing different work, different approach as well. So, but anyway, the quantum theory provides an elegant way to formalize those kind of intuitions. So that's contribution. So we have 2 publications to specifically talk about those. And because the time limit, I want to go quickly along this, because today really is the overview, and we can go over this more tomorrow afternoon as part of the mathematical workshop to show those applications. And Emmanuel has done some of those. And the paper has really the paper I cited here, for example, the first paper to show those kind of ideas, really, yeah, really has done this. But I want to mention is that actually, for example, in this 2013 paper and later the more application, the PNAS paper, actually we didn't have zero parameter estimation of the model. It's just a conceptual model, and from the mathematics, from very simple assumption and mathematics, we derive a equation. Like I will show you in a second. So I'm going to skip this those slides, because this is very similar to what Emmanuel was saying. Basically, you're in a vector space, you project, right? Project based on the question, and then you produce those kind of order. And actually, the order can be produced to expand many, many different ideas. I use some of those ideas. This I can talk separately, but I want to come back to like, how do we test it, right? How do we know it's good? It makes sense, but how do we know it's good? So this is what we did. So from very, very simple assumption, this theory is so simple. If you just believe, you project to A to B, you project to B to A, and following the quantum rules, then you will derive something we call QQ equality. Basically, it says probability say yes to question A, no to B, plus probability to say no to A and yes to B. You know, this doesn't make sense, right? I would never think about this psychologically, but it's just mathematically derived. This two adds up should be equivalent to when you say yes, no, no, yes in the other order. This is weird, right? Psychologically, I would never derive this hypothesis. But based on this very simple assumption of the model, without fitting the model, so it's parameter free, we have to have this. And it's extremely testable because those are just empirical data. So it's dimensional free, it's parameter free. We don't depend on fitting the data. Then we tested this using some experiments, some existing data, and it all worked very well. It's very different question, like Clinton-Gore question, asking other candidates, ask you dislike white people, dislike black people, you know, like hostile. This is very interesting, especially in the current social problems, right? So this racial tense between different races, actually it's very interesting. I can discuss more this example later on, asking some celebrities, and we did experiments in my lab as well to have better control. But it all supports this QQ equality. So we all found actually there are other effects, but then there are QQ equality. So this support is very extremely the highest level kind of test about the theory in social behavior science in our view. So then later on, then say, hey, this can we test this more? So I went to David Moore and also actually to get more data, but also went to Pew Research Center. So now we have this QQ equality, very simple, extremely testable, because you just grab a few, you don't need any math. You only need like a kindergarten math to do this in a way, maybe. So what we do is that now we have this prediction. It's so testable, it's scarily testable. Now let's just go to get the data that's possible out there to test it. So one thing we did with with a student solo here who now works in the industry, we went to the Pew Research Center without any prior judgment. Just try to find out in the past 10 years, whatever questions have this kind of ABBA question built in their design, right? So it's their data collected and it's national representative data and so on. So we are able to secure 70 surveys with a lot of help and with a lot of work on our own, because the data are available out there, but it's hard to identify the proper ones. So we got a national representative sample. So each sample is always nationally representative, and the mean is at least 1,600 people. And then we also did 2 lambda experiments. So then we did a test on this. And so this is citation if you want to read this, because there was supplemental material also compared to some other explanations that come up from really thanks to those people give challenges to the theory. So we try to address some of the challenging questions and competing models. But anyway, basically in short words, simply speaking, that there is a significant order effects across all the 72 studies, and the QQ equality is supported, which is like doesn't make sense. Even Q equality like, psychologically doesn't make sense, but it's just has to be true based on that model mathematically. So okay, I just want to quickly summarize. There are several ways we can test model, right? So test model in our way. We don't have those luxury physics, those equipments, advanced equipments in physics, but we only have, a few possible. We collect the data and so on in social behavior science. But one way is like what I just showed, like maybe derive and some novel predictions, right, from the theory. Luckily, we can do that and then develop the QQ equality as an example to test the theory. Those probably is really preferred because it doesn't depends on any parameter you feed, because we always feed a model, always do better model. So the second way is more traditionally what we do with model comparison and model development. Then we can parameterize the model, and we did so. We parameterize this kind of model I just mentioned to even to a dynamic way to read the scale measure. So it's not binary, it's to any kind of points of measure, and using a dynamic random walk model, and test using empirical data too. So this is the second way you can test a model, at least in cognitive science, is that you test the model using the best fitting parameter, and there are many established ways you can do model comparison, roughly really basically based on how the parsimony of the theory, because the theory is good when it's parsimony and can fit the data, right? Because that's one problem maybe with machine learning nowadays. We fit the data so well, but the data is not parsimony, and it's so hard to interpret those coefficients and parameters. So, but But anyway, so the second way is testing our version, the quantum version of the psychological model against those competing traditional models. And the truth is that sometimes, right, you develop, because the changes that you have to find the empirical data, for example, finding those survey questions, and then you have to come up with a competing model, because maybe there is not a classical model developed yet. So the psychology, in other ways, the psychology intuition can be very similar, but you implement one based on classical way, one based on the quantum rules, and then compete them using the empirical data to see which is using more parsimonious model to explain the goodness, to fit the data. Right, but also the parameters are extremely, different from, I think, a lot of large machine learning practice right now. So maybe that's exactly why it's useful to, really useful, important to implement, maybe implement cognitive model, including quantum model or classical model, to those bigger AI and machine learning models. So because the parameter you estimated is very informative of your theory, of your substantial questions. So it can quantify the states, how the initial state is not being, but becoming, right? Because you keep projecting the Hilbert states becoming. And the relationship between those measurements are crucial. The relationship, for example, between Gore, your trust to Gore and Clinton, or you think about one race to another, you think about one religion, because I know a lot of attendees are in the field of religion, one religion to another, right, could quantify their relationship in this black box of mind. That's very hard to really know by self-report alone. So relationship between the measurement, the individual difference is another interesting one. So Emmanuel mentioned this as well. People can change, depends on people can think differently because their capacity, because they're training properly. And in my own practice, I found about 1/3 of people, they are more classical. About 2/3 people are more quantum-like. So, but anyway, so to predict updates and dynamic mental states and so on. But anyway, so, but also, another way to leverage is that it's really is important to derive new predictions. For example, again, using the same example, because I'm trying to use this very simple example here. For this ABBA question order, you can derive a null parametric test. You can parameterize it and do model comparison, and construct interesting questions to enrich and quantify and specify your theory. And you can derive new ideas. Again, this shows how important to have criticism and challenges from the field, right? So actually, this A prime paradigm is in response to criticism to people on hypothetical experiments, especially the group of people have physics background, so it's a sort experiment. Say, if it's A, B, and BA, but that makes sense, because if you ask A and B, A question and B question, then you ask A, because this, how would it interfere at all or not? Anyway, some challenges, the sort of experiment they did, it wouldn't matter. So it's fair, it's really fair, right? Because, I don't know. So why not just gather data and test it? So we did. So it's, instead of thinking about this experiment, let's just do it. So then we gather data using Paradise. So it's published here in 2017. But actually, it's really interesting because in test is A, you ask question A, ask B, and ask A again. We derive something really interesting based on the uncertainty principle. But now in the context of psychological measurements, it's quite interesting. But anyway, I don't want to go back. There was just a ton of fantastic work, and Emmanuel has presented a lot. And again, I want to encourage you to especially read Emmanuel, Pathos and Busmaya's review paper from last year. It's really nice updated review about the field. And there are many more. And some of those are really more specific to cognitive questions, like violation of rational decision, interference effect, and this and that, right? So it's like based on quite typical paradigm, the categorization and decision paradigm, for example. But so we're starting to think maybe we should make this more general, as more something like kind of based on psychology ideas, but also more like a statistical model. So people with a lot of different questions, applied questions, can use this kind of model. So that's what we did and published in these 2 papers here. And it's what we call Hilbert space multidimensional model, HSM model. So this kind of hybrid of a statistical model, something in between. If you think about the model as a continuum with statistical models, it has nothing to do with your specific theory of human mind or whatever. It's just statistics. And the other is the cognitive model, which is very much tied to your cognitive or behavior theory. And here's in the middle, has some of this intuition and implementation about how people make judgment, make decision, make human measurements, but it can be applied more generally to all kinds of questions. So that's one of the efforts. So basically, this is a data fusion problem. That's what's more common now with big data practice. Because we got the data, we merge them. They have all kinds of contexts that are being connected. For example, maybe it's 2x3x2 type of matrix with A-B question, but A can also be collected. This measurement can be collected, a question collected, question measurement collected being observed in an ABC kind of context. So it's a 3x2x4 kind of context. Then quickly you'll see this is something Emmanuel mentioned already. If you're using Bayesian methods, then the dimensionality explodes quickly, right? Because the dimensionality can really go quickly. And then, for example, in this simple example here, we have AB, A collected in context of C, A collected in context of BC, A was measured in the context of CD. Then at least in this example, you need ABCD joint distribution for Bayesian networks. And it's quite a large dimensionality. But Hilbert space multidimensional model make it much more maybe simpler in a way. So it doesn't require actually against the idea about the joint distribution if they are incompatible, right? Those ABCD measurements. So we had the empirical data again in both papers and lay out, like the cycle review paper is also more tutorial-like, to lay out the steps to develop those kind of model, to use those kind of model for your questions. So it's very general to research questions and extremely testable because we also develop ways you can test whether there are those kind of sequential effects, contextual effects occurred. And the parameters are meaningful. So it's not like just feeding the data. They're meaningful to tell you what you can know in the context of, for example, A in B, in C, in D, in BCD, and so on. But anyway, this is just a start and of those kind of journey, and I want to summarize that why it's useful. It's just one of the ways that it has some advantage to provide a coherent theory, not generalized. I have to be careful in saying this, but in some sense, generalize classical probability, because at least in this, probability aspects of it, when the measurements are compatible, it works quite much like a classical, like Emmanuel mentioned, maybe Bayesian, some like local Bayesian, and so on. So they introduce some very interesting new concepts to or back to psychology, right? So like the compatibility, superposition, those ideas. And the quantum probability theory provides a viable new way to model probabilistic and dynamics of human cognition, behavior, and maybe society. and it provides a very coherent way for many, many different puzzling violations of the classical probability. That's found in a variety of literature. This has never been collected before. I think this is amazing. Because beyond the data feeding and parsimony of theory, it's very general too. It forms a new foundation for understanding widely different phenomena using a common set of axiomatic principles. Also, we like it because it's axiomatic. It's well established, but of course, there are many other ways I want to emphasize. There are other statisticians and logicians develop other probability theories, especially subjective theories to be able to do modeling too. But I think they're all good ways, and it's just up to us to see maybe in which context is it better. And using, to me, I feel we need to use empirical data to test them, definitely. So hopefully it can be applied to many other questions. That's really making a lot of breakthrough right now. Yeah. So here we just illustrate two ways we can empirical testing idea. It's extremely testable. I want to emphasize that because it's coherent, self-contained. So if you say something is compatible, then it entails uncertainty principle. So it just have to be, right? You can't be just compatible, but now uncertainty principle doesn't work. So it's extremely compatible. Oh, sorry, extremely testable because when you be able to, test the idea about compatibility, a range of other principles and rules and testable ideas follow. So yeah, just to summarize again, at least our practice to do those kind of empirical testing of those kind of models is can use the non-parametric way or parametric way. Thank you very much. Sorry, I took a little bit long, but I do have the opportunity again, 1 o'clock and tomorrow afternoon, and of course, anytime, right? Anytime over email, any other Zoom to chat. Thank you very much. Thank you.
Thank you, Joyce. Would you like me to moderate the session?
Yeah, that would be wonderful.
Okay.
Yes,
so we have one question in the chat, and so please feel free to submit your questions. So since you mentioned these ABA type of experiments at the end, which I find very interesting, it reminded me of a comment. I think it came up last year by Atmansbacher. I'm not sure, but the role of non-commutativity, the potential role, also when it comes regarding the way we perceive time. So because if there's, you can only tell that AB is different than B, no, AB is different than BA if there's a time direction. So this was an interesting observation because usually our usual way of thinking about time is like given by the direction of increasing entropy, like more entropic time. Whereas here, if there's a type of order effect in the way cognition works, this could indicate another mechanism to generate a feeling of time. So I wonder whether you can comment on this.
That's a really big question, very hard, very good question. I think we haven't done, at this level, meaningful. I think Professor Hoffman probably can chime in, the space-time, right? Exactly. This is kind of really intriguing and interesting, but I don't know I have good answer. Empirical, in the empirical way. I have some thoughts about this AB and BA, but I guess ABBA, I don't know. This can tell. I don't know. I'm sorry. I don't recall whether Harold at my spec was asking this contest, but I don't know. This can whether this can touch some deep question in sense. In my part ABBA, I haven't thought about this with whether it can collect with the test about perception time, error of time, or maybe the bad, not necessary or wrongness Professor Hoffman was saying about time space, but I think it's really interesting, big thing psychology itself, again, we do have a lot of study about temporal decision making, for example. And there are, yeah, you know, you think about maybe not about ABBA, but you think about me today and me next year. You know, kind of, I guess I don't have good answer to this just because I kind of think about the empirical way how to test this using this ABBA. But I definitely think it's something myself is intrigued also. Okay, let me say one thing, probably even irrelevant to you, because time is so interesting and so, no matter it's relevant, exist or not. But you know, people, for example, people multitasking, then they feel time pass by really much faster, the perception. But maybe this touches to the capacity. It's one way to lower the capacity of perception about time is not there anymore. Then people more or less in that mental state for the primary task maybe is in a more incompatible way. I'm worried to say that because it depends on how we model it. Yeah, but it's really a good question. But I guess it's so big and I don't have good empirical way to think of really how we can test it. But I think Emmanuel has maybe comments and follow up or question.
Thanks, Joyce. Thanks, Michael. So just very briefly, I wanted to mention that when it comes to time, people have tried to test these violations of these temporal Bell inequalities. And to make a long story short, if these are violated, then essentially across different time points, it's not possible to specify well-localized states. That is, our classical notion of time is that, say, at time point 1, and then 2, and then 3, there is a sort of like well-ordered sequencing. But if these temporal Bell inequalities are violated, this sort of well-ordered temporal sequencing goes away. We can't, in a way, we can't have locality in time. Now, there are a lot of like phrases here, which are quite evocative and probably make us think of something more important than it really is. But essentially, it boils down to having incompatibility between the same question at different time points, which means we can't really be certain. Say, let's say our question is whether I enjoy cornflakes, right? Something very simple. You know, and you can sort of examine this question at different time points. And if you find this inequality is violated, it means that the answer to this question at time point 1 and 2 and 3 are incompatible. That is, I can't know them concurrently. And being certain about one creates uncertainty about the others. There's a bit of a literature that are developing around this issue. Like Joyce was saying, Harald at Mansfahera has done some work on this, and we did a little bit of work recently as well. But again, like there are some phrases there which probably make people think of this as more important than it currently is. It's quite sort of very specific and perhaps not quite as, we've not been able to sort of develop it to something more general for the time being. Also, there's Jeremy Manning. There is a researcher who's a memory researcher who's recently proposed that a sort of memory has like a wave-like structure, and he built a sort of quantum-like model around it, which come for very interesting ideas. But we still quite a few steps away from a proper model. So anyway, just wanted to add to the comments that Joyce offered.
Very interesting. Who was the name of this researcher?
Jeremy Manning.
Manning. Okay, good. Okay, thank you. So let's go to the question raised by Shmuel in the chat, in the Q&A. He's asking how empirical testing of quantum models of cognition, decision, and communication can support improvement of social justice and social and economic well-being and resilience.
Good question, but a very big question. I think maybe I'll take the approach. I think Professor Don Hoffman yesterday mentioned maybe this as well. I think I take the same approach, is that first maybe we should know what's going on with us, and then we can maybe think about ways to prevent or intervene or somehow, right? For example, I was just thinking, I'm just like, this is really important and bigger question. But for example, if we know, for example, the public opinion can manipulate in this way, right? So we should be careful about how we interpret and how to do public opinion and also using those as data, because for example, in America, right, like those kind of public opinion is very informative in terms of influencing big things, because that's also related to, for example, perception about social norms and how the world, this whole country is thinking, and promote people, encourage people, motivate people to vote or not to vote, for example, or voting in what kind of things, right? So it can be very influential. I guess this is just a bigger question that to any people who study, I guess, more basic questions in in cognition, psychology, right? It's like always we want to understand how it works, then maybe we can know how it's being applied and being used for. Like for example, even work with not right now, people exploring the merge into cognitive model with large language models, but will that be bad or good? I don't know. Like those tools developed, it can be good or bad, and we have to be careful. Yeah, I think the short question is that we have to understand maybe how humans and social and economics work, then we will be able to maybe do something about it in a more informed way. Thank you.
Okay. Alex has a question, comment or question.
Yeah, and I guess this is a little bit related to the last question that Shmuel asked. I guess I'm a political scientist, and a lot of the people here are social scientists, not psychologists. And so for any sort of sociology, economics, political science, it's kind of collective behavior that is really of interest and not the behavior of individuals. Now, sometimes individuals matter too, but collective behavior, collective patterns and dynamics are sort of the main focus. And I'm wondering, from your perspective at the kind of micro level of individuals, would you expect to see quantum effects in collective behavior too? Or would we expect to see quantum effects washing out in larger populations, decohering, and then we get no quantum effects at all above psychology? So I guess I'm wondering what that transition to the macro level would look like in your view.
Yeah, in my view, it's really an important question. I think the field is generally try to do more of that. But again, just because we start with more, just our original work is more individual based. But I think definitely even and I want to step back is that how even we work on those models for more than decades, still it's just a scratch the surface of the possibility, the potential of the theory. And even quantum theory, like I think there are large principles we should utilize. Like for example, I believe, and there is also a call, and I know some people have been trying to using some quantum field theory to study the rise and fall of city, but maybe didn't work out finally. But there was such an effort in the people with expertise with those kind of large data. And to my opinion, maybe in two level, at the simpler level, which maybe something like at the collective level, even we can estimate the population. We have those kind of model, and it's not individual based, but estimate the state of a large sample of people, maybe not as society of people around the world, but the large sample of people. And I think James Yeasley have done some work of that in some of the large public survey research for estimating those models. But that's still counting modeling. And second is again, coming, but the problem that have to coming, I think there are challenges, a few challenges. One challenge is that have to have a theory at the social level to specify, then be formalized with the quantum rules. Then we have to find out the empirical data, be able to test it against maybe other version of it. To me, anything is possible. I can imagine, but I have no expertise in those. So that's a problem, because I think this depends on expertise of the special field and develop, and maybe it's against the epistemic even belief of the people. But in my view, though, have to make the theory be able to utilize those formal advantage of the quantum theory. That's my take. Emmanuel, what do you think?
I mean, I don't know. In brief, I think the trouble is that as soon as we're talking about interaction between individuals, right? That was Alex's question, wasn't it? As soon as we start talking about the interaction between individuals, then a lot of the observables, that is so things we study, become classical. That is, for example, if we're talking about interaction between, say, Michael, Joyce, myself, Alex, right? We either do things or we don't do things. So it becomes a bit harder to see how quantum-like effects can come into play. But I mean, I suppose the only slight subtlety here is that it's possible that something that I do disturbs the system. So say Joyce says something very rude to me, right? And that disturbs the system, that disturbs me, right? And then whatever I do subsequently would be from the point of view of a person, which is slightly different to what we had before. I mean, so maybe that's a way in which things that look like incompatibility can come into play in relation to the modeling of like the interaction between individuals. But I mean, like Joyce was saying, there's not been anything along these lines yet. I mean, I suppose what we lack is some kind of like sort of quote unquote paradoxical findings that can serve as anchors that would sort of build the initial models. I mean, if you think about how quantum-like cognition started being employed in, say, decision making, the people initially focused on some kind of like big flagship results that could be offer the incentive to build the initial models, and then these initial models were kind of like stretched and cut to produce new findings. Say in political sciences or sort of group decision making or situations like this, we sort of lacked similar findings, with the exception of very simple game theory like prisoner's dilemma. So I mean, these are very interesting questions, and like Joyce was saying, I wish it were possible to offer something more concrete, but it is a new area.
Yeah, and I think like to me, it's really challenging about getting data. Actually, we have been trying this, frankly, my students too. Like for example, we are looking at things like network data, like network science, right? Just using we collect those large big data with the millions of tweets. Then but itself, it is really challenging even to quantify those data. But anyway, we have worked hard to identify using the more traditional network science approach to work on those data. But like this is challenging to me is that finding the data and the question is not just data, because that's really, I mean, the kind of question, really like which social question, like in what kind of particular question for us, for example, like in this particular example I was mentioning with that I'm working with my students is people's misinformation or information passing on social media about vaccination, like the COVID vaccination is quite interesting, and there are large data. So it's individual behavior in the network sense through the social media and spread global wise, and we're able to collect the data. Sounds cool, and we managed to code in based on some communication theory, for example. But then still, there's still one challenge in how to, because we don't want to describe the data, then how to find even the place that we can say, hey, it's so puzzling. Because right now, even for network science and some of the language model is very descriptive, like computational social science is very descriptive right now. I think it's really important. I agree, it's very much needs effort, and I'm more optimistic person. I just feel like we need to work on it. I don't have good question, but I believe is that it should show some usability, but it's challenging to find the data, find the kind of level of.
Just a final comment. I mean, part of the difficulty in political science is the data are so poor and so coarse, except at the micro level, that I'm not sure we will ever find anomalies in the sense that you can find anomalies at the individual level. And so that might consign political science and sociology to some kind of inferior netherworld where quantum effects don't happen. But I suspect there are quantum effects up and down, and so I guess I'm just curious. But anyway, we're over our time, I think. So
yes. Okay. So if you want to join the discussion, like the open discussion, Kelly just posted the link in the chat, and will start in half an hour. See you there.
okay.
Thank you. Thank you for the